So let's just quickly look at the last questions in this topic. I wanted to look at the last question here. We haven't looked at that yet. It was this question, and the last question here, which explain the effect that a catalyst will have on the reaction rate. What will it do? Increase or decrease or remain the same on reaction rate. Sorry, I know I'm just jumping in here, but it is it's a constant answer. It's always the same. The catalyst. I didn't hear. Activated complex. Yes, but we're talking about reaction rate. I suppose, yeah. But what does it do to reaction rate? Increase, decrease, remain the same?
Increases.
Sorry?
Increases.
It increases reaction rate. Because activated complex is reduced, more successful collisions. Okay? Now, what are the advantages of using a catalyst in industrial manufacturing of chemicals? What advantage does it bring to use a catalyst? Just thinking, if you were a business person producing some sort of chemical, why would you look to add a catalyst to your reaction to produce this chemical?
Doesn't that speed up the process?
For one, okay. So where I used to be able to maybe produce 20 kilograms of a certain substance per day, I can now maybe do 30, because every day per unit of time I'm producing more. Obviously that's a good thing. Okay, what else? So it increases the reaction rate, but if you look at the previous question, it also did what with energy? What does the catalyst do to energy?
Doesn't it shift the activated complex?
It reduces the activated complex. What is the activated complex? Again?
Activated complex is when bonds are broken down.
Yes, it is the energy that we need before bonds are broken. Okay, now, why is it favorable that is lower? What for the experimenter does that change? For the person conducting the experiment or less energy is needed. Now that's, for me as someone that's producing a chemical, that is a good thing, because however I'm adding energy, let's say I'm using a stove, I don't need to use such high temperatures, so I'm using less energy. It reduces my production costs and increase my yield, the amount of does that make sense?
Yes.
Okay, let's look at this question. A sample of pure hydrogen fluoride is sealed. Okay, the moment you know it's sealed, then you probably know we're going to do equilibrium, because we're in a closed system in a 3 cubic decimeter container, and they give me a temperature, and it decomposes to the following balanced equation. So we have hydrogen fluoride, and it decomposes into hydrogen and fluoride. The graph below shows now here you need to notice something important. They give you the reaction rate. Look, before, this is a graph of the reaction rate. Before we looked at graphs of the concentration. Okay, I actually disagree with this. No, I don't. Okay. Initially, the reaction rate for the reactants is the highest, because it is decomposing, and because all of the volume is only hydrogen fluoride in the beginning, it is the only one that has any reaction rates. But as it's decomposing, slowly but surely the hydrogen and fluoride is increasing in concentration. And as they increase in concentration, their reaction rate is also increasing. Do you understand? And what happens at this point? Equilibrium, because both of them now have the same reaction rate. Doesn't mean they have the same concentration. If we looked at the concentration graph and it reached the same, it meant they had the same. Half of it was hydrogen fluoride, half of it was the product, or half of the reaction. This is not saying that. This is saying at some point the forward reaction and the reverse reaction is the same for both. Okay. And as you can see, the reaction rate is what I read off here. The reaction rate is never zero. There's still reactions happening, but the two reactions are happening at the same place. Then we see something happening there. Okay. What can you see? What actually happened here? You don't have to tell me what caused that, but what can you see what happened?
There's a decrease.
In whose reaction rate is the decrease?
The forward reaction.
Yeah, in the reactants. Okay. All of a sudden, that reactant rate is decreased. What could have caused that? What are some of the causes for changes in reaction rate? There's three causes.
Pressure, temperature, concentration as well.
Okay, so we're working with gas, so it's volume. Okay, so either a catalyst was added or taken away. Okay. Both reaction rates decreased. Okay, but it can either be catalyst, temperature, or a change in concentration. Okay, or volume, but I think it would make sense. If I take away a catalyst, I think the effect on both would have been the same. Do you agree? Because the catalyst favors the forward and the reverse reaction the same. So the reaction rate decreased, which means I took away something, or I took away the catalyst. Or the second thing would be I took away temperature. I took away heat. Now let's just quickly see what will happen if I take away heat. This is a what type of reaction? Endothermic or exothermic? Endothermic, because so in other words, if it's endothermic, heat is a product. So if I take away heat, a reactant, sorry, I'm just speaking. If I take away a reactant, who am I going to favor? The forward reaction or the reverse reaction?
If you take away a product,
If I take away a reactant,
wouldn't the reverse reaction?
the reverse reaction, because now all of a sudden the products are in excess. Okay, now look at this. The effect on who is the biggest. Now remember, reaction rate for both will decrease if I take away heat, but it will affect who the most, the forward or the reverse reaction.
Forward.
It will affect the forward reaction the most because you've taken away one of its reactants. So can you see how this makes sense, that at this point heat was taken away? Both of the reaction rates decreased, but it had the biggest effect on the forward reaction. Okay. And now at this point, they start reaching equilibrium again. I'm not exactly 100%, I don't feel comfortable with that answer now, because when I originally answered this question, I said at this change, I would say that that hydrogen fluoride was removed from the container. Okay. But if hydrogen fluoride was removed from the container, I would favor the reverse reaction, which means the forward reaction will decrease and the reverse reaction will decrease, the forward reaction will increase. But here it makes sense to me, because this one also fell, that it was temperature. But I think both of them could actually be a correct answer. Because if I do take away, it wouldn't change the the reverse reaction rate. If I take away this, it wouldn't have that immediate effect. It would only have had that small effect. But I must say that's now being obscuring it a little bit for me. Okay, well, let's quickly read what they ask. Write down the meaning of the term irreversible reaction. What would you say is a reversible reaction?
The products can go back due to being reactants.
Okay. How does the concentration of reactants change between the 12th and the 15th minute? So between the 12th and the 15th minute, how does the concentration of reactants change?
Does not change.
It doesn't change. The reaction rate forward. The rate of both the forward and the reverse reactions suddenly changed time T15. Give a reason for the sudden change in the rate. Now I'm fairly convinced it's temperature. But my original answer when I answered this question was a change in the concentration. Because usually, but that's because I didn't really note, I did see its reaction rate, but I didn't really consider what change that would have. If this was a concentration graph, concentration versus time, then it's a sudden change like that, not unless it's a sudden change in all of that. In all of them, a sudden change would have been, if all of them had a sudden change, it would have meant the volume was all of a sudden changed. And both of them are all of a sudden changing, but this one with a little. So it doesn't make sense. They would have both had the same change if it was volume. So it's not volume. Give a reason for the sudden change. So I would say this is temperature, and here I would explain my reason would be because both the reaction rates decreased, which means temperature was decreased, but since temperature is a reactant, it had the biggest effect on the reaction rate for the forward reaction. So that would have been my answer here. The pressure on the system is increased. Use Le Chatelier to explain the effect that this will have on the equilibrium system. Here we notice that a change in pressure will not cause any stress, because if I increase the pressure, the moles of gas on the left and the moles of gas on the right is the same. So despite adding a stress to the system, there is no side that would be more stressed than the other side. So I suppose I would say it like that. Okay, now the equilibrium constant for the forward reaction is, so they give us the equilibrium constant. At equilibrium, it is found that this many moles of hydrogen fluoride is present in the container. Calculate the concentration of F2, okay? Okay, so my Kc value would be the products, which in this case is hydrogen and fluoride, their concentration divided by the concentration of hydrogen fluoride. Okay, the concentration of hydrogen fluoride they did give me. They didn't give me the concentration. They give me the amount of moles. So I already know that at equilibrium, this one is at 0,4 mole, and now I just need to know what's the concentration, and so I need to go and look at the size of the container. Well, let me rather do that. So the concentration of hydrogen fluoride would be equal to the moles divided by the volume, which is 0,4 divided by the volume of the container. 0,4. You're clever, huh? You remember well. 0,04. Okay, I'll fix it now. My container is 3 cubic decimeters. So 0,04 divided by 3 cubic decimeters, and that gives me 0,0133. 0,0133 repetitive. Okay. I'm not 100% sure about this one, but I suppose then that hydrogen, the concentration of hydrogen is assumed to be equal to the concentration of fluorine. Don't know why, I don't think that's the right assumption. But they don't give me anything to go and work out. Oh, no, wait. It has to be equal because, sorry. It has to be equal, and I'll show you why. If we look at we started with hydrogen fluoride. Okay. And every 2 hydrogen fluorides produce 1 mole of hydrogen plus 1 mole of fluoride. Okay. So at any point, there's the same amount of hydrogen and fluoride in that container. Okay, because this one decomposes perfectly into 2. Now, if we started with hydrogen and fluoride, we might have started with 2 different amounts. And so it's not necessarily assumed that hydrogen and fluoride is always the same, has the same concentration. It depends on what I started with. If I started with the same amount of both, then the whole time I will have the same amount of both. But if I had, and I did start with the same amount of both, nothing. Okay, so here the ratio will be the same the whole time. For every, the change will be 1:1. So, in other words, this comes down to 0. Was it 0,12? I think so. 0,12 is equal to. So these 2 values are the same. So I could, instead of hydrogen, since I don't know hydrogen, I can say, well, it's also equal to fluorine. And fluorine is equal to itself divided by the concentration that we worked out here of 0,0133. And so now if I multiply both sides, on the one side I have now that fluorine squared is equal to, this was 0,04 over 3, that's now multiplied with 12, which is 3 times 4, so these cancel, so this is 0,16, and so fluoride, if I take the square root on both sides, I should get 0,04 mole per cubic decimeter. Okay, sorry guys, this is stretching. I just want to do calculate the equilibrium constant for the reverse reaction.
Wouldn't it be equal?
No, because what's different if I look at it from reverse? In terms of the formula, Kc is products over reactants. So if I look at it from reverse, What changed? Okay, for time's sake, I'll say my products and reactants are different way around.
This is like the inverse.
It's the inverse. So now that 0.4 is actually 4 over 100. So the inverse of that is 25. 100 over 4. Okay? So this would be an example of something with high yield. Okay, I think there's one more question there. The temperature is now increased to, and it used to be that, it's increased to that. How will the value of the equilibrium, the Kc, for the forward reaction change? What will happen to the Kc value?
Increase.
Well, we have to go look at it first. We have to look at whether it's an endothermic or an exothermic reaction. It's an endothermic reaction. I can't just tell if you increase or decrease. I have to work it out. So it's an endothermic reaction, which means I'm increasing, if I'm increasing temperature, I'm increasing reactants, which means my existing reactants will decrease. My products will increase. So my Kc value will increase. So yeah. So if it was exothermic, it would have had the opposite effect. Okay. Then, per your request, I'll do one more. Okay, so this was last year's Sakai question. The following graph represents the concentration of reactants and products against time during the formation of biodiesel and ester from soybean oil and triester. So don't let these things confuse you guys. If you don't recognize these things, doesn't necessarily mean that you missed out studying. Okay, ignore things that might upset what you think about the question. So I have no idea what's a biodiesel or soybean oil or triester. I've never heard of that. Okay, the reaction is run at 50 degrees Celsius using 20 sodium hydroxide solution as a catalyst. This is all just to confuse you. With an initial molar ratio between methanol and triester at 3.1. Okay, so your methanol and triester started at 3 versus 1. So for every 3 moles, we'll have 1 mole of the other one. And the ester and glycerol ratio at 3 to 1. Okay. Then, what does this say? Equilibrium. Then this should have had a reversible arrow. Excellent. So here they just give us our concentration versus mole graph. First question, I'll try and answer this as far as I can just on here. How long does it take for the reaction to reach equilibrium for the first time? Roughly, what do you think?
Just after 20 minutes.
20 minutes, really? No, look there. There's still, after 20 minutes, there's still a gradient.
30.
Did you say 30? Okay, sorry if you did. I would even see, even here at 30, this thing is still going down.
So
I would say 34, 35, roughly there. Anything less than this thing isn't flat yet. Okay, so try and be as accurate as possible. It's better to go a little bit further than back. Why is the amount in moles of methanol that reacts more than that of the triester? So if we look at the methanol, okay, where's the triester? Look at methanol. Look at the change. It goes all the way from there way down here, while the triester just goes like, and they're asking why. Okay, I'm not going to waste time because according to my reaction formula, I need 3 methanols for every 1 triester. So each second or for every reaction, 3 methanols are used for every 1 triester that's used. Okay, stateless Chatelier's principle, can do that. The equilibrium was disturbed at 60 minutes. So let's go to 60 minutes. Here's something happens. What can you see changed visibly immediately?
Methanol increased.
Methanol all of a sudden increased. So what change was made? No, methanol was added. Just more methanol was added. Okay, that's it. Okay, what caused this disturbance? Okay, state the factor and the effect on the equilibrium. So methanol was increased, so all of a sudden we have more product, reactant. Now, which is going to be favored, forward or reversed? Forward reaction. So more products are going to form, and look there, here's the products, those that start at 0, and at this point a little bit more of this formed, a little bit more of that formed, and a little bit more of the triester is used. You notice that? Okay, and so after a while they reach equilibrium again. Explain your answer in question 64 in terms of Le Chatelier's principle. So according to Le Chatelier's principle, the reaction will counter the stress. So since the stress was added to the reactants, more products are formed. Okay, calculate the Kc value. Oh, this is actually a lovely question because it's not difficult. The Kc value at 50 degrees for this reaction at 35 minutes. So if we go to 35 minutes, Kc value would literally be mole of, sorry, here. The Kc value is the concentration of what? Of the ester and glycerol. The ester and glycerol. And don't forget your exponents, because that's where it actually came in. There's 6 marks, but it's really not difficult to say 6 marks. There's your ester has an exponent of 3, glycerol exponent of 1. Divided by the concentration of methanol and triester. Okay, and again we need to look at the triester is 1, the methanol 3. So 3 and 1. And now, where are we going to get the concentrations from? From the graph. It's quite easy actually. So at 35 minutes, they've reached the equilibrium the first time. So for the ester, it looks at about, what is that, 2. So this is 1, 2, 3, 4, 5. So it's 0.5, 6, 7, 8. 1.8 for the ester, and for glycerol it looks at about 0.6. So this is 1,8 to the power of 3 times 0,6 to the power of 1. And for the other ones it is at 1,4, and this one at 0.2. So 1,4 cubed times 0,2 to the power of 1. And that's entering into your calculator. That's actually lovely, huh? Easy question for 6 marks. Okay. Cool. Let's see if we can answer a few. Here's another one. I'll just quickly read through it. A certain amount of nitrogen dioxide gas NO2 is sealed in a gas syringe at 25 degrees. When equilibrium is reached, the volume occupied by the mixture in the gas in the syringe is 80 cubic centimeters. The balance equation of the reaction takes place. So in other words, nitrogen dioxide decomposes into dinitrogen tetraoxide, okay, and this one is dark brown while that one is colorless. Okay, define the chemical equilibrium. At equilibrium, the concentration of that NO2 gas is that the equilibrium constant for the reaction is 171 at 25. Calculate the initial number of moles of NO2 gas placed in the syringe. Okay, so at equilibrium, we have at equilibrium, our Kc value is given as we've got our N2O4 divided by NO2. So our Kc value is 171. NO2 is unknown. For NO2 is given a concentration of 0.2, which means the concentration of N2, sorry, and I forgot my, this must be to the power of 2. Okay, and so the concentration of N2O4 at equilibrium is 171 times 0.04, 171 times 0.04, 70.84. That doesn't look right. 171 times 0.04, 6.84. 6.84 mole per cubic decimeter. Okay, so that's the concentration of, and that's not what they're asking. Okay, but all I know is what was the moles that I that I have at equilibrium of nitrogen dioxide. Okay, but that's not how much I started with, because some of it decomposed. So for example, initially I don't know how many moles I started with. Okay, I do know how many moles I started with of the dinitrogen tetraoxide. Nothing. Remember what they said in the beginning? A certain amount of nitrogen dioxide is sealed. So I had nothing of the other one. Then I see, okay, but at equilibrium, okay, this is the ice table. At equilibrium, I have 0.2 moles of this one, and I've got 6.84 moles of this one. So I know that, that's not how many moles I have, that's how many mole I have per cubic decimeter. So if so in other words, I know the concentration. If I want to know what 6.84, if I want to know how many moles I have, and also this is not, if I want to know how many moles I have, I must actually, so once again I just want to show you, I don't do my calculations on my concentration or on my grams, I do it on my moles. So I keep converting I have to convert into moles. So if I know the concentration of nitrogen dioxide, I can go and dinitrogen trioxide, the volume is given as 80 cubic centimeters, which again must be divided with 1,000. So mole is this times 0.08 is 0.5 0.5472. So that's how many moles 0.5472. That's how many moles was added. 72. But now look at the reaction formula, NO2 N2O4. Look at the reaction formula. For every 1 mole of this, 2 moles of that is used. In other words, if this one increased with that much, how many did this one decrease with? Twice that. Does that make sense? So minus 1,5 4, so 0, 9, 4, 4. Double that. Okay? And so, and then at equilibrium, how many moles do I have? I know how many moles I have per cubic centimeter. So 0,2 cubic decimeter, sorry, is how many moles is that of 0,08. If I multiply that, I get 0,016. Point 8 times 0.0. Sorry. 0.08 times 0.2 is 0,016. That's right. Okay, so that's how many moles I have in the end, 0,016. So in other words, this is the equation I'm trying to solve. I started, I don't know with what, and then I used up double the amount of moles that I produced, okay, which is 0,0944, and I ended up with 0,016 moles. So in other words, x is equal to 0,016 plus 1,90944. Plus 1,0944 equals 1,1104. 1,1104. Let's just see. This is now in moles. I've been calculating moles. Let's just go back and see if that's what they ask. I can always calculate moles. Just use the information they give me, convert into moles, do my calculations, and then once from there, let me go and look what they're actually asking. Once I have moles, I can, at equilibrium, the equilibrium can calculate the initial number of moles. That's what they wanted. For 8 marks, it's not bad. Okay. Diagram, a mixture in the syringe after equilibrium is established. So here's the equilibrium at 80 cubic centimeters. The pressure is now increased by decreasing the volume. So now, they push down on this. The pressure is now decreased. A constant temperature as illustrated in the diagram. Okay, so they illustrate. Immediately after increasing the pressure, the color of the reaction mixture in the gas syringe appears darker than before. Give a reason for this observation. Okay, so and again, I'm sure you guys can figure it out. But if it is dark, that doesn't make sense. Immediately after the increase in the pressure, the color in the reaction mixture in the gas appears darker than before. Give a reason for this. It does make sense. If most of the space is being occupied by the dark brown, because it occupies 2 moles of space versus 1 mole. So most of the space is occupied by the dark brown. So if I decrease the volume, initially the molecules are still spread out. So the dark brown is lighter because it is occupying more volume. So the moment I'm increase that, the same amount of brown now occupies less space, so it will look darker. Does that make sense? That's immediately after I have not reached equilibrium yet. Now, once I've pressed it slowly but surely, the reaction starts taking place. And now, when I increase the pressure, okay, I'm increasing a stress on the left-hand side because it takes up most space. So it tries and produce more of the colorless. And so afterwards, after a while, a new equilibrium is established as illustrated. The color of the reaction mixture in the gas syringe now appears lighter than the initial color. Okay, use Le Chatelier's principle to explain that. And that is because the equilibrium was shifted to the right, so that more of the colorless gas is present than before. Okay, the temperature of the reaction mixture and syringe is now increased and a new equilibrium established. How will each of the following be affected? The color in the mixture, will it be darker or lighter? So it now depends, am I going to shift to the left or to the right? This is a endothermic, exothermic. Exothermic, which means heat is a heat product or reactant? A product. So if I increase heat, I'm increasing products, which means which reaction is favored? Reverse. Okay, so reverse is favored, so will it become darker or lighter? Darker. Okay, so darker. The value of the equilibrium constant, what will happen to the value of the equilibrium constant? We've already now figured out which one is favored. Reverse is favored, so I'm producing more reactants or products. More reactants, which means numerator or denominator increase. Denominator increases. Products are reactants in the denominator. If the denominator increases, Kc decreases. Okay, so Kc value will decrease. For temperature, it will always change. Anything else, it will not change. Only temperature changes Kc value. Guys, Kc values to calculate it, these longer questions, these 8-mark questions are usually difficult for students. So go and practice them because they really are not. Okay. You are going to get one, so might as well try as many as you can.